Properties of gases. Gases differ from solids and liquids in the following ways. 1. A sample of gas assumes both the shape and volume of the container. Think about it, when you put ice cubes or water in a glass, those don't fill up the glass. They will only fill up as much as you put in it. But if you put gas into your glass, it will fill up the whole glass. 2. Gases are compressible. 3. The densities of gases are much smaller than those of liquids and solids and are highly variable depending on temperature and pressure. And 4. Gases form homogeneous mixtures or solutions with one another in any proportion. All of these properties can be explained by the kinetic molecular theory. The kinetic molecular theory. The kinetic molecular theory explains how the molecular nature of gases gives rise to their macroscopic properties. The basic assumptions of the kinetic molecular theory are as follows. 1. A gas is composed of particles that are separated by large distances. The volume occupied by individual molecules is negligible. 2. Gas molecules are constantly in random motion, moving in straight paths, colliding with perfectly elastic collisions. Elastic collisions being if two things hit each other at the same speed, they will bounce off at the same speed as they collided in. 3. Gas molecules do not exert attractive or repulsive forces on one another, i.e. when these gas molecules fly by each other, they don't even say hi to each other. They pretend as if they don't exist. And 4. The average kinetic energy of a gas molecule in a sample is proportional to the absolute temperature. So in other words, kinetic energy is proportional to temperature. The higher the temperature, the higher the kinetic energy of each gas molecule. So how do all of these assumptions fall into place in reality? Well, let's look at it. Gases are compressible because molecules in the gas phase are separated by large distances. This is assumption 1. Pressure is the result of the collision of gas molecules with the walls of their container. This would be assumption 2. Decreasing volume increases the frequency of collisions, and therefore pressure increases as collision frequency increases. Think of it this way. If you were to run in a room, every time you hit a wall, that would be pressure. Now, if you were in a large room, it would take you a longer time in between collisions to create pressure. So there's going to be less collisions per unit time. Whilst if you were in a tiny room, you would collide with the walls a lot more often. This would be an increase in pressure. Heating a sample of gas increases its average kinetic energy. This is assumption 4. So gas molecules must move faster if the temperature is increased. Faster molecules collide more frequently and at a greater speed. Therefore, pressure increases as collision frequency increases. If you were running around a room, the faster you went, the more times you would hit the walls. The kinetic molecular theory and molecular speed. The total kinetic energy of a mole of a gas is equal to 3/2 ideal gas constant times temperature. The average kinetic energy of one molecule is half times the mass times the mean square speed. So therefore, for 1 mole of a gas, it is the Avogadro's number times the kinetic energy of one molecule, which equals 3/2 ideal gas constant times temperature. If we rearrange this, we get this equation in the bottom right of the root mean square speed, which is the square root of 3 times ideal gas constant times temperature divided by the molar mass of the gas. The root mean square speed, or URMS, is the speed of a molecule with the average kinetic energy in a gas sample. The root mean square speed is directly proportional to temperature. As you can see in this graph, the number of molecules with higher molecular speeds increases as the temperature increases. Interestingly enough, the root mean square speed is also inversely proportional to the square root of the molar mass. So as the molecule gets bigger, the speed decreases. in this graph here, we can see that as the molecules become heavier per unit mole, the number of molecules with fast speeds decreases. When two gases are at the same temperature, it is possible to compare the root mean squared speed values of the different gases. It is done by using this equation here. This equation should give you a ratio between two gases where you would say that one gas is, say, 1.5 times faster than the other. Diffusion and effusion. Diffusion is the mixing of gases as the result of random motion and frequent collisions. Effusion is the escape of gas molecules from a container to a region of vacuum. Graham's law states that the rate of diffusion or effusion of a gas is inversely proportional to the square root of its molar mass. This makes sense as we know that the speed of a molecule is inversely proportional to its mass. Alright, let's have some fun. Determine the molar mass and identity of a diatomic gas that moves 4.67 times as fast as carbon dioxide. Well, we can use that equation that relates to speeds at the same temperature and pretty much work backwards from this ratio. So we can use the equation below to determine the molar mass of the unknown gas. How? Because we know the molar mass of carbon dioxide, which is 44 grams per mole. We also know that this equation equals 4.67. So if we put those numbers into the equation, we can solve for the mass of the unknown. When you plug it into the calculator, you'll find out that the mass is 2.018, or just 2, which means that this gas must be hydrogen gas. Fun times indeed. Gas pressure. Pressure is defined as the force applied per unit area, i.e. pressure equals force divided by area. The SI unit of force is the Newton, where 1 Newton is 1 kilogram times meters per second squared, whilst the SI unit of pressure is the Pascal, defined as 1 Newton per square meter. However, there are a bunch of other units of pressure that are not quite SI units but have their place in science. We have the standard atmosphere, ATM, which is usually the pressure at sea level, where 1 atmosphere is 101,325 pascals. We have the millimeters of mercury, which was used in barometer measurements, where 1 millimeter of mercury is 133.322 pascals. A torr, which was a name given to millimeters of mercury in honor of Torricelli, the inventor of the barometer, has the same value. And finally, the bar, which has the same order of magnitude as atmospheres, but is a decimal multiple of pascals, i.e. 1 bar is 1 times 10 to the 5 pascals. Pretty much just rounds up the atmosphere instead of having to use the 101,325. Just call it 100,000. So how do we measure pressure? A barometer is an instrument that is used to measure atmospheric pressure. Standard atmospheric pressure was originally defined as the pressure that would support a column of mercury exactly 760 millimeters high. The equation for this definition was pressure equals the height in meters times the density of the mercury in kilograms per meters cubed times G, which is the gravitational constant of 9.8 meters per second squared. Because of this, 1 atmospheric pressure at sea level ends up being 760 millimeters of mercury, or 760 torr. This, of course, leads to the weird values of 760 to be the only exact values, and of course 1 atmosphere being the equivalent. However, the pascals and the bars and the psis have to be calculated. PSI being pound per square inch, a not very standard unit in the sciences. But what if you're not interested in atmospheric pressure? What if you want to know the pressure inside a container? Well, at that point you need a manometer, which is a device used to measure pressure other than atmospheric pressure. And that's it. Moving on. The gas laws. Boyle's Law, the pressure-volume relationship. Boyle's law states that the pressure of a fixed amount of gas at a constant temperature is inversely proportional to the volume of the gas. So V is inversely proportional to 1 over P. This leads to the equation pressure 1 at volume 1 equals pressure 2 at volume 2 at constant temperature. Or in other words, if you decrease the volume, the pressure will increase, and if you increase the volume, the pressure must decrease. Although the relationship between pressure and volume does not seem to be perfectly linear, if we look at volume versus the inverse pressure, you will see that it is perfectly linear. Let's try this concept out. So calculate the volume of a sample of a gas at 5.75 atmospheres if it occupies 5.14 liters at 2.49 atmospheres. So assuming at constant temperature, we are given one pressure and we are asked for a volume when we are given another volume and a pressure. So we should use P1 V1 equals P2 V2. Voila. So we want to solve for V2 when P1 equals 2.49, V1 equals 5.14, and P2 equals 5.75. We plug the numbers in and we find out that the volume is 2.26 liters. All it is plug in the numbers and it chugs out the answer. Charles and Gay-Lussac's law, the temperature-volume relationship. Charles and Gay-Lussac's law, or simply Charles's law, states that the volume of a gas maintained at a constant pressure is directly proportional to the absolute temperature of the gas. What do we mean by that? We mean that if we have, say, a balloon at a regular temperature, if we cool it down with, say, liquid nitrogen, the balloon will deflate even though the amount of gas in it stays constant. Or even more simply, colder the gas, the less space it occupies. You might have encountered this with your tires flashing low pressure when it's really cold outside. If volume is directly proportional to temperature, we can use this equation to figure out changes in volume as temperature is changed, or if the temperature changes, what would be the difference in volume? Note that this is also a pretty effective way of calculating what absolute zero is, because all volumes should converge to zero at a minimum temperature, which is negative 273 degrees Celsius, or as you may know, 0 Kelvin. I will point it out right now that when you do these calculations, you are better off always using the temperatures in Kelvin. If you are given temperatures in Celsius, make sure to convert them into Kelvin. So let's test it out. A sample of gas originally occupies 29.1 liters at 0 degrees Celsius. What is its new volume when it is heated to 15 degrees Celsius? We gotta assume constant pressure. Well, the equation that we know that compares volume to temperature is this one. We have to convert our temperatures into Kelvin, so we add 273 to both of them. We are also told that volume 1 is 29.1, so we are just solving for volume 2. We plug in the numbers, and we will find out that the volume would increase from 29.1 to a total of 30.7 liters. That is an increase in volume of 1.6 liters, which is relatively significant. Fun times indeed. Avogadro's law, the amount to volume relationship. Avogadro's law states that the volume of a sample of a gas is directly proportional to the number of moles in the sample at constant temperature and pressure. So V is proportional to the number of moles. We can use an equation which is V1 over N1 equals V2 over N2 at constant temperature and pressure. Interestingly enough, as this relates molecules and moles to volume, we can look at the stoichiometry of an equation and relate that to the ratio of volumes. For example, in this reaction here, if we have 3 hydrogen gases reacting with 1 nitrogen gas to give us 2 ammonium gas molecules, the ratio is 3 molecules plus 1 molecules gives us 2 molecules, which would be the equivalent of 3 moles of hydrogen plus 1 mole of nitrogen giving us 2 moles of ammonia, which when converted to volumes would just be 3 volumes of a gas plus 1 volume of a gas gives us 2 volumes of a gas. So the change in volume would be from 3 to 2 equivalents. So let's see it in action. What volume in liters of water vapor will be produced when 34 liters of hydrogen gas and 12 liters of oxygen gas react according to the equation below? So the stoichiometry states that 2 moles of hydrogen will react with 1 mole of oxygen to give us 2 moles of water. Well, if this is the case, we have 3 units of volume forming 2 units of volume. Well, what is the total volume of the starting materials, or the 3 units? Well, it's 34 liters plus 17 liters, giving us 51 liters total volume. Well, that is 3 units is 51. We go down to 2 volumes of water vapor, therefore we do 2/3 of 51, which ends up being 34. So, where do we go from here? Well, let's look at examples of how changing the pressure, volume, or the amount of material can have an effect on a system. Let's see what happens if we change the temperature of a gas at a constant volume. Well, as you will notice, if we decrease the temperature, the pressure will also decrease. Whilst if we increase the temperature, the pressure will increase. If we wish to maintain the pressure constant, then if we lower the temperature, the volume will decrease, whilst if we increase the temperature, the volume will increase. The presence of additional molecules does cause an increase in pressure. So for example, if we have a system with molecules, if we remove molecules from it, the volume will have to decrease to maintain the same pressure. Otherwise, the pressure will decrease. Whilst if we add molecules to the system, the volume will have to increase to maintain pressure constant. All these factors can be combined into one equation. The combined gas law, the pressure, temperature, amount, volume relationship. The combined gas law can be used to solve problems where any or all of the variables change. This equation is P1 V1 over N1 T1 equals P2 V2 over N2 T2, where P is pressure, V is volume, N is the amount of your material, and T is your temperature. This is another standard equation of plug in the numbers and the answer pops out. The ideal gas equation. The gas laws can be combined into a general equation that describes the physical behavior of all gases. If we take Boyle's law, where volume is inversely proportional to pressure, Charles's law, where volume is proportional to temperature, and Avogadro's law, where volume is proportional to the number of moles of the gas, you can end up with a proportionality of volume is proportional to the number of moles times temperature over pressure. If we convert this proportionality equation into a real equation by adding a proportionality constant, in this case R, called the ideal gas constant, we end up with an equation of V equals R NT over P, which we can rearrange into PV equals nRT. This is the ideal gas equation. The ideal gas equation, PV equals nRT, describes the relationship among the four variables pressure, volume, amount of gas, and temperature. An ideal gas is a hypothetical sample of a gas whose pressure, volume, temperature behavior is predicted accurately by the ideal gas equation. The gas constant R is the proportionality constant, and its value and units depend on the units in which pressure and volume are expressed. So here are various expressions of the gas constant. The ones you need to know are 0.08206 with the units of liters times atmosphere per Kelvin times moles. This is very standard because a lot of your pressures will be given in atmospheres. However, the other one you need to know is 8.314, which is joules per Kelvin times moles. Another one that you will encounter a lot. So how do you know which one to use? Well, it really depends on what values are given in your question. If everything is given in atmospheres, then you should probably use 0.08206 as your value for R, whilst if everything is given in joules, then you should probably use 8.314. And when I say should, it's more of a have to, because if you use the wrong one, you will get the wrong values. When you see standard temperature and pressure, STP, this means a special set of conditions where the pressure is 1 atmosphere and temperature is 0 degrees Celsius or 273.15 Kelvin. If these are the conditions stated, then the volume occupied by 1 mole of an ideal gas is 22.41 liters, as shown in the equation at the bottom. Using algebraic manipulation, it is possible to solve for variables other than those that appear explicitly in the ideal gas equation. So what we mean by that is if we start with PV equals nRT, we can rearrange it to be N over V equals P over RT. If we go on to multiply both sides of the equation with molar mass, we will end up with density on the left-hand side and pressure times molar mass over RT on the right-hand side. This is pretty nifty because now we can calculate the density of a gas from pressure, temperature, and molar mass. For example, what pressure would be required for helium at 25 degrees Celsius to have the same density as carbon dioxide at 25 degrees Celsius and 1 atmosphere? Well, first we need to figure out what the density of carbon dioxide is at 25 degrees Celsius and 1 atmosphere. Well, we use the equation shown and we plug in the values that we need. Pressure is equal to 1, molar mass of carbon dioxide was 44, R will be 0.08206, and we will have to convert temperature into Kelvin, so 25 plus 273.15. Once we have these values, we plug them into the equation to give us a density of about 1.8 grams per liter. Now that we have a density, we gotta solve for the pressure and use the mass of helium because that's what we are originally working for. What pressure would be required for helium at 25 degrees Celsius to have the same density as carbon dioxide? As stated, we just solve for P instead by inputting all the other numbers, and we find out that the pressure will be equivalent at 11 atmospheres. Cool beans on toast. Real gases, factors that cause deviation from ideal behavior. As stated, the ideal gas law is about ideal gases, but turns out not all gases behave ideally. For example, in this table here, you will see that chlorine and ammonia both have lower volumes than ideal gas. How is this possible? Well, it's because at high pressure, molecules are close together and individual volumes do become significant, as opposed to originally the assumption being that gas molecules have negligible volume per molecule. Also, at low temperatures, molecules are moving slower and any intermolecular forces become significant. Think about it. Our assumption was that gas molecules fly past each other, completely ignoring each other. But at lower temperatures, some gases will have partial charges that attract to each other, causing the gases to collide with each other more often and stay closer together. If we want to have an equation for real gases, we have to take these interactions into account. In other words, we have to modify the equation PV equals nRT. The van der Waals equation. The van der Waals equation is useful for gases that do not behave ideally. So for example, it is PV equals nRT but with a corrected pressure term and a corrected volume term. The pressure value has to be an experimentally measured pressure and the volume is the volume of the container your system is in. Notice that there are two new letters in this equation, those being A and B. These are van der Waals constants. Here is a table containing some of the van der Waals constants for most common gases. You will notice that they vary between each other and are very specific and unique for each gas. If you wish to solve the van der Waals equation, you have to use the appropriate van der Waals constants for the gas that you are discussing. These two graphs show the compressibility as a function of pressure for several different gases in the top one and nitrogen at different temperatures. You will notice that, for example, ammonia, NH3, at first you can compress ammonia much more readily than an ideal gas, but after a while the ability for you to be able to compress it decreases and your compressibility value increases. Whilst most things such as nitrogen and methane compress only a small amount and then you start getting resistance. Whilst on the bottom, you will notice that as the temperature increases for nitrogen, the closer it behaves like an ideal gas. These are nice depictions showing that most gases behave uniquely and are not ideal gases. Gas mixtures. Dalton's law of partial pressures. When two or more gases are placed in a container, each gas behaves as though it occupies the container alone. For example, if you have 1 mole of nitrogen gas in a 5-liter container at 0 degrees Celsius, it exerts a pressure of 4.48 atmospheres. If we add 1 mole of oxygen in the same container, it will also exert 4.48 atmospheres of pressure. The total pressure, though, will be the sum of these two pressures, which is 8.96 atmospheres. But both gases apply that pressure of 4.48 atmospheres independently. Dalton's law of partial pressure states that the total pressure exerted by a gas mixture is the sum of the partial pressures exerted by each component of the mixture, i.e. P total equals sum of the P components. What this means is that if we have a mixture of two gases, but we know how much one of those gases is causing pressure by itself in that same volume, then we can figure out how much pressure is being created by the other component in the mixture occupied in that same volume. I.e., if you had 1 atmospheric pressure of hydrogen gas in a container and you added unknown amount of nitrogen gas, but the pressure increased a certain amount, that increase in pressure is directly proportional to the amount of nitrogen gas you added. And you could calculate how much nitrogen you added. So with a picture, each component of a gas mixture exerts a pressure independent of the other components. The total pressure is the sum of the partial pressures. Gas red has a pressure of 4, yellow gas has a pressure of 5, so you will have a total combined pressure of 9, and Bob's your uncle. As you can do this with pressure, you can also do it with moles. Mole fractions. The relative amount of the components in a gas mixture can be specified using mole fractions. Mole fractions, shown as chi, are equal to the number of moles of a certain component divided by the total number of moles present. There are three things to remember about mole fractions. 1. The mole fraction of a mixture component is always less than 1. 2. The sum of mole fractions for all components of a mixture is always 1. And 3. Mole fractions are dimensionless because the units cancel out. As the number of moles and pressure are proportional to each other at a specified temperature and volume, the mole fraction can also equal the pressure fraction over the total pressure. Furthermore, if we multiply the total number of moles by the mole fraction, we will get the number of moles of said component. Whilst if we take the mole fraction and multiply it by the total pressure, we will get the partial pressure of that component. Fancy stuff. But moving on. Reactions with gaseous reactants and products. Calculating the required volume of a gaseous reactant. So, for example, if two carbon monoxide molecules are reacting with one oxygen molecule to give you two carbon dioxide molecules, well, the ratio of combination of carbon monoxide to oxygen is 2:1. This applies to both moles or volume, as it's all happening in gas phase. However, if you had this second reaction of two sodium metals reacting with one chlorine gas, we would have to use the ideal gas equation for that one gas reactant. You would have to calculate how many moles or equivalents of the chlorine gas you are required to use in the reaction. So for example, if we are starting with 1 mole of sodium, that means that we will need half a mole of chlorine because it's a 2:1 ratio, and use that half moles amount in our PV equals nRT equation, rearranged of course to solve for V, so nRT over P, to give us the volume of chlorine we need for this reaction. Similarly, we can figure out how much of a gas is being used up in a reaction by modifying the equation. Although there are no empirical gas laws that focus on the relationship between number of moles and pressure, it is possible to rearrange the ideal gas equation to find the relationship, i.e. the number of moles equals pressure times volume over the gas constant times temperature. The change in pressure in a reaction vessel can be used to determine how many moles of gaseous reactants are consumed. So for example, the change in moles is equal to the change in pressure times the volume over the gas constant times temperature, assuming that the volume and the temperature are remaining constant. If a gas is being consumed, you would expect the pressure to decrease. Why? Because the number of moles is decreasing as the reaction is proceeding. What about partial pressures? Well, the volume of gas produced by a chemical reaction can be measured using an apparatus like the one shown below. Here you have a test tube connected by a hose to a container full of water being held upside down. As gas is being formed, it flows through the tube into the water and gets collected inside the upside down container. This gas will now push water out of the container, hence we are able to collect the gas. When gas is collected over water though, the total pressure is the sum of two partial pressures. It is the collected gas plus the vapor pressure of water. Water is always forming gaseous water by just evaporating. The vapor pressure of water is known at various temperatures, for example shown in this table here. We have a neat little row of temperatures compared to the vapor pressure created by that water at that temperature. Note that, for example, this table, the pressures are given in torr. Therefore, if you wanted to use these values in an equation, you would have to watch out and use the gas constant with torr in it in its units. So not the standard 0.08206 or 8.314. The torr one will be one of the different ones. Just pay attention to your units.